As wireless technologies evolve, our world has become more and more connected since the first generation of wireless technology. 1G connected us through mobile phone calls, 2G lets us text for the first time, 3G connected our mobiles to the internet, and 4G gave us the reliable connections we have today. However, as 4G has started to reach its peak capacity due to the increasing amount of users and the Internet of Things revolution, 5G has emerged as to overcome the limitations of previous generations. 5G is not just a mobile device or a technology. Instead, it is the backbone that will lead to various applications such as virtual reality, smart cities, smart homes, autonomous driving, and much more that has yet to be discovered. 5G utilizes an unused high radio frequency spectrum in addition to the radio frequency spectrum that is currently being used by 4G LTE. This is so that it can handle up to 10,000 times more traffic than the current network. What this means is that there is a greater bandwidth to accommodate large number of devices, low latency less than 1 millisecond, and better speeds of up to 10 gigabytes per second, which is actually 10 times faster than the current 4G. In this video, we will talk about the implementation of 5G in Internet of Things, focusing on its application layer and some real-life use cases of these implementations. The Internet of Things refers to the interaction and communication between billions of devices, providing the ability to share information related to real-world subjects through a unified framework. It is achieved by seamless, ubiquitous sensing, data analytics, and information representation with cloud computing as a unifying framework. Common technologies that enables IoT applications are radio frequency identification and wireless sensor networks, which are low power and easier to implement. There are different types of IoT that can be applied through the use of 5G. For example, the first one, machine-to-machine communication. It is the dominant discourse used by IoT, which involves peer-to-peer communication. Another example is massive machine-type communication, also known as massive IoT. MMTC pertains to services that usually span massive numbers of devices, generally sensors and actuators. These are latency-tolerant systems, and the individual data generated is minute and can be applied on low bandwidth and lossy pipes. And finally, there is the critical machine-type communication, refers to applications such as unmanned robotic surgeries, driverless cars, automated transit system, control of critical infrastructure for industrial process. The reliability and precision requirements of such services are huge and indispensable. Today, we will look at some of the requirements and network architecture in the 5G application layer that is used for application and optimization of the IoT network. As a service-driven network, 5G deploys an end-to-end network slicing architecture which aims to provide flexibility and efficiency towards diversified mobile service requirements. As so, software-defined networking and network functions virtualization is implemented to support the underlying physical infrastructure of IoT devices and also to split the 5G IoT network into small manageable parts for easy management. At the same time, 5G enables cloud access and transportation of the connected devices. Hence, cloud adoption improves compatibility for diversified 5G IoT services and enables the key technologies of E2E network slicing, on-demand deployment of IoT, and component-based network functions. In E2E network slicing, software-defined networking and network functions virtualization is used by 5G IoTs. The SDN network is directly programmable. Therefore, the network control plane can be decoupled from the network data plane, which significantly simplifies network management. SDN helps cellular operators simplify their network management and enable new services to support the exponential traffic growth envisaged for 5G networks. As so, IoT devices can be easily added or configured in an existing 5G IoT network through flexible orchestration and plug-and-play deployment. This flexibility offered by SDN can enable fine-grained resource control to enhance users' experience while in the meantime maximizing network utilization for 5G IoT networks. A NFV management framework provides network registration, identification, and management to build virtualized network functions. Through NFV, logical control functions of 5G IoTs can be extracted as independent functional components that can be flexibly combined according to service requirements. Network status information of individual IoT devices can be stored in a centralized database and accessed by other devices as metadata within the network without signaling overhead for data synchronization. All these components will implement a standard representational state transfer services interface to build NFV applications to inter-device communication. Standardized frameworks will aid in lower cost, simpler implementation, and promote new feature integration in an IoT network. At the same time, independent features ensure that the addition of new devices and potential upgrades do not affect existing network services. In QoS management for 5G Internet of Things, the QoS parameters such as delay, jitter, losses, bandwidth, reliability will be stored in a database in the 5G mobile devices. Intelligent algorithm running in the mobile terminal will use these parameters as system processes to determine the wireless selection to be selected. Therefore, upon required QoS and personal cost constraints, the best wireless connection will be provided for the 5G IoT devices to optimize network efficiency and availability. The mega landscape of IoT demands efficient trust models to manage the security and sanctity. Given the huge users, man and machine both, authentication becomes a primary factor of concern to prevent unauthorized access to confidential user data used or generated by the IoT devices. In 5G, end-to-end security is responsible to ensure integrity, confidentiality, and availability of data. E2E security architecture provides differentiated security protection, which is designed to cater to different vertical industries. In our cases, the design of security protection needs to consider how to fulfill various security requirements of different IoT devices within the network. Nonetheless, the E2E security has great flexibility in order to provide better support and rapidly align with changes in the IoT network. By using end-to-end privacy protection, we can fully safeguard our IoT network, leaving no part of the security chain vulnerable to privacy leaks. In mobile edge computing, the data generated by different kinds of IoT devices can be processed at the network edge instead of the typical approach of transmitting it to the centralized cloud infrastructure to decrease bandwidth and energy consumption. Mobile edge computing can provide services with faster response and greater quality in comparison with cloud computing by enabling applications and services to be hosted on top of the mobile network elements, which is on the application layer. MEC is suitable to be integrated with IoT in 5G networks to provide efficient and ensure services for a large number of end users, as these applications and services can benefit from being in closer proximity to the customer and from receiving local radio network contextual information, which will decrease latency. When 5G and IoT combines, it can be used in our daily lives to provide convenience. For instance, 5G IoTs can be used in delivery systems such as Amazon Prime Air. Unmanned drones are designed to safely get packages to customer within 30 minutes after an order is placed. At the same time, Starship Deploys is currently on trial to use unmanned robots for delivery and has recently partnered with Just Eat to deliver food to people's door. When a fridge has been transformed into a 5G IoT, it may detect the use of stored items and even place online orders to replenish the finished items automatically. Also, corporations and government could use different types of services such as smart parking transportation, intelligent lighting, water metering, waste management, and environmental monitoring to enhance our living quality. As 5G is promising the low latency in network, the study on tactile internet has been carried out to enhance virtual reality and haptic feedback through the network, which may bring us to the future of augmented reality. The rapid growth in a variety of access devices and end users demands causes IoT to drive a digital transformation in all aspects of our current modern lives. According to Cisco, the number of devices connected to the IoT will be added to 50 billion by the year 2020. Although 5G is still in its early stages, it is developing in full force, and the vision of an internet for everyone and everything comes closer to reality every day.